This is the intro video to section 1.3, measuring segments. This is part 1 of section 1.3, and our objective for this video is to find and compare lengths of segments. Okay, so as we're going through here and we do this, we're going to talk about some new postulates, and we're going to be able to find lengths of segments and compare lengths of segments. All right, so remember a postulate is a statement of fact, if you remember from section 1.2. So postulate 1.5 is what we call the ruler postulate. It says that every point on a line can be paired with a real number. So point A right here, I can put a real number to that. Point B right here, I can put another number to that as well. This makes a one-to-one correspondence between the points on a line and the real numbers. In other words, that means that this point A is the same thing as maybe 3. And this point B is in the place of 5. Okay, that's essentially what that means. The real number that corresponds to a point is called the coordinate of the point. So if I were to say this point A right here is 5, that's its coordinate. And this point B here was 7, that's its coordinate. Okay, that's what the word coordinate means. Coordinate of A, coordinate of B is putting a number value to it. So the ruler postulate allows you to measure lengths of segments using a given unit and to find distances between points on a number line. If you consider line AB over here to the right, okay, the distance between points A and B is the absolute value of the difference of their coordinates. Now, there's a key word here, difference. Okay, remember difference means to subtract. So I'm going to put down here subtract as a reminder that that's what difference means. Difference means to subtract. Okay, so we find the difference of the two values. For example, a quick example, let's say I said this happened to be 6 and this happened to be, let's say 12. Okay, if I wanted to find the distance from 6 to 12, you could do it this way. You could take 6 minus 12. And 6 minus 12 is negative 6. But you'll notice distance is always going to be positive. Okay, so that's why they include the absolute value. And the absolute value makes everything positive, which tells me the distance from 6 to 12 is 6 units. Now, on some problems, you're going to be able to count this. So you can be able to, if they have tick marks like this here, you could count it. But not every problem is going to be that way. So you're going to have to be able to use that formula a little bit. Okay, so let's take a look down here and let's go through some examples. It says here, what is ST? Okay, so what that means is it's asking how far is it from S to T. And if you look at your number line, okay, there's two ways essentially you can do this. You can count from the mark starting and count each tick mark. That's absolutely a possibility. So you start here at negative 4. You're counting by 2, so there's 2, there's 4, there's 6, there's 8, there's 10, and there's 12. So in this case, ST, and they're asking for the length of it, okay, ST would be 12 units long. Okay, 12 units long. Now, as we're going through here on this, you could also do it this way. You could find the coordinate of ST. So we can say segment ST is S is at negative 4, and we're going to subtract T, which is at 8. And we're going to take the absolute value of it. Negative 4 minus 8 is negative 12, and if I take the absolute value of negative 12, that gives me positive 12. Because the absolute value, again, measures the distance a number is from 0. And you'll notice you get the same number as you did when you counted. Okay, some are going to be easy to count, some are going to be easier to find the distance, okay, using the formula. So, what are UV and SV on the number line above? So UV, segment UV, letter U is at the point 10, V is at the point 14. So if I take 10 minus 14, and I'm going to use the absolute value, 10 minus 14 is negative 4. Absolute value is going to make it positive 4. So UV is 4 units long. Okay, and if I want to find SV S has a coordinate of -4, and I'm going to subtract V, which is 14, and I'm going to take the absolute value. Okay, and then I do that, I get the absolute value of -18, and -18, the absolute value of -18 is +18. So the distance from S to V, the length of that segment is 18 units. Okay, now the other way you could do is you could count it. So let's take SV for example. You start at S and you count by twos because it's by twos this time. 2, 4, 6, 8, 10, 12, 14, 16, and you could do it to 18 as well. So you could always count by hand as well. Okay. All right, so that talks about measuring segments. Okay, next we're going to talk here about postulate 1.6, which is the segment addition postulate. This is a very, very important postulate. You're going to use this postulate for a lot of the year. Okay, and what this postulate says, and I'm going to zoom in here a little bit so you can see a little bit better. It says if 3 points A, B, and C are collinear, so that means they're on the same line, A, B, and C. And B is between A and C, so B is in between the two. It's not in the middle exactly, but it's in between the two. It says then AB plus BC is equal to AC. So in other words, kind of a fancy way, that's a fancy way to say it, I could say this part right here, plus this part right here equals the whole. So when we talk about segment addition postulate, we want to take the one part, plus the other part to equal the whole. Okay, part plus part equals whole. AB is one part, plus BC is the part on the right, AB is the part on the left, and that's going to equal the whole thing, which in this case is segment AC. Okay, that's what the segment addition postulate will say. You're going to use this quite a bit. So, it says here, when numerical expressions have the same value, you can say that they are equal. Similarly, if two segments have the same length, then the segments are congruent segments. Okay, what's the difference between congruent and equal? Really and truly and honestly, they mean the exact same thing. It's all about how the notation is. Okay, so as you look here at this first example on the left, you'll notice they say equal here, and they have measurements. It has a number that's measured. Anytime they use numbers, you're going to say that they're equal. Okay, so these two, A, B, and C, D, are equal to each other because they actually have a measurement. Over here on the right, you'll notice that these don't have a measurement. We don't know how long CD is, and we don't know how long AB is. But you see these tick marks. And what these tick marks mean is that they're the same. Okay? So since they don't actually have a value, we say that they're congruent. So segment AB and segment CD are congruent to each other. Essentially, they mean the same thing, but it's determined on how they label it. So if they label it with a number, you use equals. If they label it with a marking, you use congruent. Okay? And that's essentially what this says here at the bottom. Okay, so let's go through let's take a look here and let's go through some examples. Okay? Let's go through here, and we talked about our AC and BD congruent. Okay, so we got to figure out, first of all, how long they are. So we know that how to figure out how long they are. So we'll figure out here AC from A to C. We've got 2, 4, and 6, and then one more, which is 7. So AC is 7 units long. Okay. If I really wanted to do the actual math with it, I'd take the absolute value of -2 minus, in this case, C's at 5. Okay. And you would get AC to be 7. BD. Again, sometimes it's easier just to count. B starts at 3. Okay. So I go 3, there's 1, and then 3, 5, and 7. So again, that's 7 units long. Again, you're counting by twos, but if they're in the middle, it's only from 1 to the next mark. So are these two congruent? Okay, are these two congruent? Yes, they are. Segment AC is congruent to segment BD. Now, some would ask, well, Mr. Klein, you used measurements here, or you used actual values. They didn't show the value in this graph. We didn't show that it was 7 units long. We had to actually calculate that. Okay. All right, so you can figure out, again, to finish up here, I want you to complete this problem. So put a star next to this guy, because I want you to do that one on your own. So I'm going to save some time here, and I want to look at some of these other examples. All right, let's take a look here now at this example using the segment addition postulate. It says EG is 59. So what it's saying here is the whole segment EG is 59 units. What are EF and FG? I want to know what these two pieces are. Okay, so again, part plus part equals the whole thing. So I want to set up an equation. The left side is 8x minus 14. And if I add that to the right side of 4x plus 1, it has to equal the whole of 59. So left plus right equals whole. Okay, and now I'm going to solve this equation. So 8x and 4x are like terms on the same side of the equal sign. I'm going to combine these guys. So I've got 12x's total. Okay, and I've also got negative 14 and I've got positive 1 on the same side, and that gives me negative 13. That equals 59. Okay, now I need to solve for x. I need to get x by itself. So in order to do that, I got to move the 13 to the other side, so I'm going to have to add 13. And when I add 13, 12x equals 72. And when I finish this off, since this is multiplication, I have to do the opposite, which is division, and x is going to equal 6. Now, as you look at this, is 6 my answer? Well, it asks the question, what are EF and FG? So it's asking, I want to know how long these are. Not, I don't want to know what the variable is. So in order to figure that out, I got to plug these back in. So 8x minus 14. I've got 8 times 6. Minus 14. 8 times 6 is 48. Minus 14 is 34. So EF, EF is 34. Then I got to look at 4x plus 1. So I've got 4 times 6 plus 1. 4 times 6 is 24. Plus 1 is 25. And this is segment FG. Now, what's one way to check yourself? The one way to check yourself is these two segments have to add up to be that number 59. If I add 34 and 25, it better be 59 because the two parts have to equal the whole number added together. So they do, and we've checked our answer. Okay, so that's a good example of segment addition postulate. You're going to see quite a bit of this. Now, I want you to take a look at this example as well. So I want you to do essentially, as you look at these, I want you to do this example before class tomorrow, and I want you to do this example before class tomorrow. So you have 2 examples before class. Okay. Don't forget to also complete your WSQ with this 1-3 part 1. Again, you have those 2 examples, and don't forget the WSQ. This completes section 1.3 part 1.